Hello, I'm Anubhab Ghosh, and today I want to talk about my Google Summer of Code project on efficient JIT-based remote execution. So, our two primary goals are to support small code model in the JIT, which is the default for most compilations, and also to use shared memory as a transport for the generated JIT code. So, let's begin with the description of code models first. So, code models determine what range of addresses can be used in your program. So, in the small code model, your program has to be linked in the lower 2 GB of the address space, but in large code model, it can be as large as you want. So, what is the benefit of using small code model? If you look at this assembly code of a function calling another function, we can use a relative call instruction when using small code model, as the relative address will fit within 32 bits. But in large code model, we need to load a whole 64-bit address in a register and then call it, because the compiler does not know how far away the address will be. This is also true for reads, writes, and other operations. So of course, the first one is much more efficient. So we want to support small code model for our JIT if possible. Now, before we look for a solution, let's look at another aspect, which is the transport of the generated code. So LLVM JIT supports running the generated code in a separate executor process, and they communicate using an RPC scheme known as the executor process control. This communication happens over Unix pipes or sockets, and also includes the actual generated code as well. So a better way to transfer the code is through the use of operating system based shared memory APIs. So we can map shared memory pages into the address space of both the processes. Now the JIT can directly write to the address space of the executor process, uh, avoiding unnecessary copies of the generated code. Now this reduces the number of RPC round trips that we need and the amount of system calls we need to make. And is also great for use cases where you need to transfer large data structures or huge amounts of code. Now, to achieve this, we had a two-step approach. First, we introduced the MemoryMapper interface. This is like a pluggable transport layer abstraction that it abstracts the lower level operations like interacting with OS APIs, shared memory APIs, or actually allocating memory. So we have two implementations, the inference mapper and the shared memory mapper. The inference mapper is used when running the JIT generated code on the same process as the compiler. So it can directly use the LVM size memory functions to allocate and free memory in the same address space. So this is useful when you want to run the code in same process, but if you want to run the code in a different process, you can use the shared memory mapper. It uses the POSIX or Win32 shared memory APIs to manage memory. So first it creates a shared memory file, and then it maps it on both sides of the both the processes. And this requires an executor side component as well, which is implemented in the shared memory mapper service. Now, using any of these mappers, we can build a slab-based memory allocator on top of it to solve our first code model problem. So that's exactly what we did with the mapper JITLink memory manager class. This class uses any memory mapper for actual memory operations. On the first call to allocate, using the mapper, it will reserve a large 1 GB chunk of address space from the executor, and it will return a small area from that as requested. Now, on subsequent calls, it will continue to return subregions from the same chunk while avoiding going through the EPC or making more system calls. That means further allocations are almost free. So, but more importantly, now that we allocate all our memory areas from a single chunk, we can be sure that all our addresses are within a 1 GB region or whatever we reserved. That means now we can safely use code that has been compiled with small memory model. So we have achieved compatibility with that. So how do you use this in your own project? All of this code is already in tree, and this memory manager has been integrated into the LLVM JITLink tool. So you can check out these two functions in this file for an example of how to use. Using shared memory is a bit more tricky. So it requires you to enable the executor shared memory service. So you can also see an example for that. And it will also require some symbols of that service to be exposed. So those are also in the example code. So thank you for attending this session. There is a larger post with a bit more details on this link, and you can contact me at any of this.